Example 3. Let Sn represent the following statement. 1 cubed plus 2 cubed plus 3 cubed plus all the way to plus n cubed is equal to n squared times the quantity n plus 1 squared, all divided by 4. Prove that Sn is true for every positive integer n. Well, this was one of the summation rules that we saw in section 11.1. Back then, we accepted it as truth. Now, we're going to use mathematical induction to prove that this statement holds for every counting number. So, this is the particular summation rule where you're adding the first n cubes, and this is the result of doing so. Okay? So let's begin our induction process. We are, of course, going to start with the base case. So we basically need to show that the statement is true for the counting number n equals 1. So I'm going to say if n equals 1, then S1 becomes what? So look at your statement. Everywhere you see an n, replace it with 1. So this will become 1 cubed here. On the left side, we're supposed to start at 1 cubed, and we're also supposed to end at 1 cubed. So that means that the only number that will appear on the left side of the equation is going to be 1 cubed. On the right, everywhere you see an n, replace it with 1. So we're going to get 1 squared times 1 plus 1 squared, all divided by 4. We need to simplify to make sure this is a true statement. So this is going to become 1 equals 1 times 2 squared over 4. This is going to give us, or tell us that this is 1 is equal to 4 over 4. So 1 equals 1, which is true. So thus S1 is true. So we have shown that the statement holds for n equals 1. All right, moving on to parts B and C. We are preparing for induction. We're simply going to write down the statement for n equals k, and then the statement for n equals k plus 1. Going back up here, if we're looking at the situation where n equals k so that we can write down sk, everywhere you see an n, replace it with k. On the left side, we will be adding all the way up until k cubed. So the left side is going to become, and I'll write here, sk is 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed. The left side, or sorry, the right side, we're just going to replace n with k. So we're going to get k squared times k plus 1 squared all over 4. So I'm going to go and jot that down. Okay, so this is going to be k squared times k plus 1 squared over 4. All right, that is the statement sk. Everywhere we saw an n, we replaced it with k. Now, we have to write the statement for the counting number k plus 1. So what does S of k plus 1 look like? You're going to do the same thing. Go up here. Everywhere you see an n, you're going to replace it with k plus 1. Remember, when you're writing down the statement for k plus 1, you need to make sure to put the k term in there. Okay, so what's going to happen here, this left side, let me erase this. The left side is going to be 1 cubed plus 2 cubed plus 3 cubed, blah, blah, blah. We're adding up, we're replacing n with k plus 1. So we're ending with k plus 1 cubed. But you have to remember, you have to put the cube that comes before it, which is k. Okay, so the left side is going to be 1 cubed plus 2 cubed plus 3 cubed plus, we're ending on the counting number k plus 1. It has to get cubed. The counting number that comes before it is k, which also has to be cubed. The pattern here is that the numbers are being cubed. Okay, this is a must for the induction step. You have to have that there to match it up with the assumption. All right, what will appear on the right? If we go back up here, we're going to replace every instance of n with k plus 1. So this is going to be, okay, if I take this n and replace it with k plus 1, I'm going to get k plus 1 squared. And now I'm going to replace this n with k plus 1. So this is going to be in parentheses k plus 1, and then add this one. That's going to be squared. The bottom is going to be 4. Okay, so I'm going to write that down. This is going to be k plus 1 squared times k plus 1 plus 1. I'm just writing it out for your notes. That is going to be squared. Everything is going to be divided by 4. Okay, I'm going to simplify the right side here, and then I'll box it as my final s of k plus 1 here. Okay, so it's going to be 1 cubed plus 2 cubed plus 3 cubed plus, we eventually get to k cubed, k plus 1 cubed. All right, I don't have much simplifying to do here. This is just going to be k plus 1 squared times k plus 2 squared divided by 4. All right, so this boxed in black is what I'm going to have to prove in my induction step. Okay, so this is what I'm going to have to prove. All right, moving on to page 8, part D. Okay, assume that SK is true and use algebra to change SK to SK plus 1. This is the induction step. We have to start by assuming SK. Okay, so we're going to assume that we're going to flip back and write down S of K in its entirety. Okay, so let's go back up here. This is the statement that we are assuming. Okay, so I'm going to write this whole thing down. So it's going to be, we're assuming that 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed is equal to k squared times k plus 1 squared over 4. Okay, that is our assumption. Okay, just making sure it's right. All right, so now using this assumption and algebra, we have to prove the statement in part C. We have to show that S of k plus 1 is true. Okay, so the way we do this, okay, let's go back to the statement we have to prove. We are going to start by writing down the left side of the equation. Okay, so we're going to say then 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed plus k plus 1 cubed. What is that equal to? That is the left side of the equation. Okay, again, you cannot just jump to the right side and write it down. Okay, you have to start here and use your assumption and then use algebra and work it until you get the right side. Only then are you done. Okay, so let's go back over here. Now it's time to use our assumption. Okay, we are assuming that this is true. Okay, well then we're going to match it up with this left side here. Okay, we know if we add the first k cubes, okay, that's going to be this. Okay, so what I have highlighted in yellow is equal to k squared times k plus 1 squared over 4 by assumption. So what I have highlighted in yellow here is equal to this thing. So I'm going to write it down. K squared times k plus 1 squared all over 4. The stuff in yellow is equivalent. Okay, on the left side, we have the yellow quantity, but we have to add k plus 1 cubed, okay, to keep the equation balanced. Okay, so we have used our assumption. Now we're going to use pure algebra to turn this side into this right side in the equation in part C. Okay, so we have to make it look like this. Okay, I'm even going to write it down. Okay, I'm going to go over here and say my goal, just so I don't forget, my goal is k plus 1 squared times k plus 2 squared all over 4. That's my goal. Okay, when you manipulate with algebra, you've got to keep the goal in mind. Okay, all right, so what's going on here? Okay, we have a fraction, and then we're adding something that's not a fraction. So we're going to combine these guys into one fraction because that's what the goal is. Okay, so I'm going to stick this thing over 1 to make it a fraction. We need a common denominator, so multiply the denominators together. That's just going to be 4. I need to go to each numerator and adjust it for the denominator. This first term in yellow already has a denominator of 4, so I'm going to leave the numerator alone. And then I'm adding in the middle. Okay, we have a 1 in the bottom. We want it to be 4, so I'm going to multiply the denominator by 4. So since I did it to the bottom, I have to do it to the top. So the new numerator is going to be 4 times k plus 1 cubed. Okay. All right, so now we've got one fraction. Okay. And we have to, again, keep manipulating it until it turns into this. Okay, we're on the right track because we have one fraction with a denominator of 4. Okay, it looks like we're gonna have to do some factoring in the top. Okay, so notice one of the factors is k plus 1 squared, which I see right here. Okay, so what I'm gonna do, I'm gonna kind of adjust the numerator here. I'm gonna leave the first term alone. And then on the other side of the plus sign, I'm going to rewrite this as 4 times, if you have k plus 1 cubed, you can write that as k plus 1 squared times k plus 1. Okay, so now I've got a k plus 1 squared popping up here and 1 here. They're common, and so we can factor it out of both terms. Okay, so in the numerator, I'm going to factor out a k plus 1 squared. That's going to leave me with k squared plus 4 times k plus 1. Okay, the bottom is still 4. Okay, we're getting there. Okay, I'm going to simplify what is in the brackets here. Okay, this is going to be k plus 1 squared times k squared plus 4k plus 4 if I distribute the 4. Okay, the bottom is still 4. Okay, don't forget the goal. Look at what I need to end up with over here. Okay, we're almost there. I see a match right here and I see a match right here. We just have to turn this other thing into what we need. Okay. All right, so we are manipulating this guy in the brackets. Okay, it can factor. Okay, I'm going to leave the k plus 1 squared alone. I'm going to leave the 4 alone, and you can factor this thing in brackets. Okay, I'm going to write it in red so it stands out. Okay, it will factor into k plus 2 times k plus 2. You can distribute the two factors in red to make sure that that is correct. If you FOIL, you're going to get k squared plus 2k plus 2k. Those will combine to give you the 4k, and then 2 times 2 is 4. So that is awesome. Okay, and then our last step here, we have k plus 1 squared, 4 in the bottom, but the two red factors are the same, so we can just say that it's the same thing as k plus 2 squared. Okay, that is exactly our goal. Okay, we have reached the the right side of the equation in part C, so we are done with the induction step. Okay, I'm going to do a little summary blurb right here. Okay, I'm going to say this final result is the statement for n equals k plus 1. It has been shown that if Sk is true, then S of k plus 1 is also true. Okay, done with the induction step. In part E, we need to write a conclusion for the entire problem. In part A, we did the base case, proved that the statement held for n equals 1. In part D, we did the induction step that if we assume it for some positive integer, then the statement will also be true for the next counting number. So we just summarize the 2 steps required for proof by mathematical induction have been completed. So Sn, the statement Sn, is true for every counting number n. We are done with the proof.